So let's look at a demonstration problem here that actually is a little bit involved. It'll take a little bit of time to solve, but it does a good job of employing a couple of our equations that we've used so far. So let's say I have a projectile and it's launched straight up at 60 meters per second from a height of 80 meters at the edge of a sheer cliff. The projectile falls, just missing the cliff and hitting the ground below. So this is the situation we have. We have an object, and I'm going to diagram it, and then I'm going to write down the givens. So my initial velocity here, I'm going to indicate that that is going to be a positive 60 meters per second. I know that this delta y, and this is where you have to be a little bit cautious, the delta y ends up going to be a negative 80 meters. Okay, it's actually ending up below where I started. I know that acceleration due to gravity is going to be negative 9.8 meters per second squared. That's a friend I can carry with me all year long. And I know that the velocity at max is going to be 0. Those are things that I know. Okay, so what questions might we have from this? We could ask, what is my maximum height? How long does it take to hit the ground? And what is my final velocity when hitting the ground? Okay, so let's take each of these in turn. Now there are a couple of ways we could solve that first one. For the first one, we could say the equation that I could use would be VF equals VI plus AT, but unfortunately I don't know the time here, so that equation doesn't end up being very good. But what I can use is my equation without time. VF squared equals VI squared plus 2A delta y. And what I'm going to do is I'm going to rearrange and know the fact that at maximum VF equals 0. So I can say that 0 equals VI squared plus 2A delta y. Now what I'm going to do here is I'm going to toss this over to the left hand side, because what I want to really do is figure out what this delta y is all by itself. So I'm going to try to isolate that. So I'm going to say that negative 2A delta y equals VI squared. And I'm going to keep riding down the primrose path here. I'm going to say that delta y equals VI squared divided by a negative 2A. So that is going to be my equation that I'm going to work with. So now what we're going to do is substitute in, whoops, let me get this back, is substitute in what we know here. And so delta y equals 60 meters per second, and I'm going to square that on the numerator, divided by a negative 2, and you have to watch your signage here. It's a negative 9.8 meters per second. So what's neat about this is that the negative and the negative offset each other, which gives us a positive delta y for our maximum, which is good. So you end up with 3,600 meters squared per second squared in the numerator, divided by 19.6 meters per second squared. And so you're going to end up here, when it's all said and done, with a delta y of 184 meters. But don't forget that you were already 80 meters above the ground. So you could either think of the delta y as being 184 meters or the y max as equaling 264 meters. Okay. So that answers the first problem. Second problem poses this situation. How long did it take before it finally hit the ground? So this is going to get a little bit meaty here, but the only equation we can really use is going to be, to solve this, is going to be V final equals VI plus AT. But again, I don't know the time, I don't know the V final, so this equation has two variables I don't know. That's not going to work too well. So I actually have to use delta y equals VIT plus 1/2 AT squared. Now this is going to get a little bit messy, but stick with me. That's the equation I'm going to need. I could rearrange it for now, but we're going to see here the fact that I have a t and a t, and that's what I'm looking for. We're going to have to employ the quadratic equation. So my delta y ends up being a negative 80 meters. My VIT is 60 meters per second times time. And I'm going to lump this together. 1/2 times negative 9.8 is minus 4.9 meters per second squared t squared. Now, unfortunately for us, is the only way we can solve this is going to be the much despised quadratic equation. So I'm going to toss all this over to one side and set it equal to 0. I'm going to say 4.9, and I'm going to eliminate these because I'm just really worried about the t, and it's going to work out. So if you'll bear with me on that. So I'm going to say 4.9 t squared minus 60t, because that is going to become a negative when I flop it over the side, minus 80 equals 0. And in the quadratic formula, we would say that this is my a value, that's my b value, that's my c value. So I'm tossing this in the quadratic equation to solve for my roots of t. I'm going to say the opposite of b, which is going to be 60 plus or minus the square root of b squared, which is 3600, minus 4a, which is negative 9.8. I'm sorry, that's not true. My a value, I'm mixing up acceleration and this value for a, times negative 4.9, okay, c times 80, all over 2a, which is 9.8. And what comes out in the wash here is that your value for t, when you solve this, ends up being 13.4 seconds. So it's a good use for that. Now, one thing to be careful of is that you actually get another root of that, another answer, because it's plus or minus the square root, but the other answer is a negative value for time, and until we invent some type of new technology, we can't go backwards in time, so that you have to discard the negative value. So now we get to the last part of the equation. What is my V final when I finally strike the ground? And so what we're going to do here, we have an easy equation for this. V final equals VI plus AT. We're going to substitute in what we know. And this one actually ends up being pretty neat. 60 meters per second plus a negative 4.9 meters per second squared times time, which we now say is 13.4 seconds total in the air. Oops. And what's going to happen is when we solve this meters per second squared times seconds, this ends up being meters per second, so we end up with our units in agreement, and our V final here ends up being somewhere in the order of a negative 71 meters per second when it strikes the ground. Okay. Now, one thing to make note of is the fact that when this ball crosses this point right here, it was going upwards at 60 meters per second. When it crosses the point where it was launched, this is going to be traveling at a negative 60 meters per second. So because it's falling at that very fast rate, it covers these 80 meters very fast. Okay, so that's one thing to kind of bear in mind there. So what I'd ask that you do for next class is to read these pages. Now that you have a textbook, so you can do these. You don't have a test Tuesday, but we will have probably a test on Friday and Monday of next week. Okay? So, hope things are going well. Please send me an email if you've got a question.